Hello. Now we will do the Kirchhoff's law. So in case of complex circuits, whether it is R circuit or in future we will learn about the C circuit or L circuit, meaning resistance circuit, capacitor circuit or the inductor circuits or the combination of these circuits. So whenever there will be some complex circuit, to solve those circuits we need some sort of a mathematical equations or the laws giving us those mathematical equations. So it's the Kirchhoff's law which gives us those mathematical equations. So there are two Kirchhoff's laws. So one by one we'll study both of them. So first we'll start with first law. So first Kirchhoff law, or first Kirchhoff law, it is based upon the principle of conservation of charge. Conservation of charge. We all know that charge is a property. It cannot be created, it cannot be destroyed. So when a particle carries a charge, it remains there with that particle. Okay, so in our case, when we talk about the circuits, it's the free electron which carries the charge. It's the free electron which carries the charge. So let's say we are having multiple wires. And there are resistances or capacitors or inductors connected with those multiple wires. And generally we apply this first law at the joints. So ultimately if there are wires, they will be meeting at the joints. Okay, so this is one of the joint I'm talking about. So at this joint, let's say the current I1 is going inside from somewhere. I'm just assuming it. We can assume it is going outside as well. So at this joint, I1 current through this wire is going in. I2 current is also going in through this wire. It's just a hypothetical thing I'm assuming. Then I3 current, I'm assuming it is going out from this wire. And there is I4 current which is going out again through this wire. So this is joint. So inside this joint, two currents are going in and the two currents are going out. Okay. So if you know about the current, we all know that current is nothing but delta Q by delta T. It is rate of flow of charge. So from this I1 we can say the corresponding to this I1 there is a fixed number of charge which is a fixed number of electron which are going inside to this point in 1 second. Similarly, corresponding to this I2 there is a fixed number of electron which is going inside to this point. And the I3 and I4, the fixed number of electron corresponding to I3 as well as I4, they are going out with respect to this point. Okay, so we all can define the charges corresponding to these currents. So what I'll do, corresponding to I1 charge, I'm defining delta Q1 charge. Corresponding to I2 current, I'm defining delta Q2 charge. Corresponding to I3, I'm defining delta Q3 charge, and corresponding to I4, I'm defining delta Q4 charge. So this delta Q1, delta Q2, delta Q3 and delta Q4, these are the charges which are moving in delta T time. It's a constant time for all these four. So in delta T time, delta Q1 charge goes in. In the same time, delta Q2 charge is going in from this wire. In the same time, delta Q3 charge is going out through this wire, and the delta Q4 charge is going out through this wire. Okay. So from this formula, if you see I is delta Q by delta T, we can get the value of delta Q1 as I1 into delta T. Since I1 will be delta Q1 divided by delta T. Similarly, delta Q2 can be written as I2 delta T. Magnitude wise, delta Q3 can be written as I3 delta T, and the delta Q4 can be written as I4 delta T. So I have defined all these four charges in terms of the respective currents and the time in which they are going inside. Okay. So we know from conservation of charge cannot be destroyed, cannot be created. So at a point the charge remains fixed, and at a point we can assume the charge is zero. So initially there was zero charge at this joint. So then in delta T time, delta Q1 charge went in, delta Q2 charge went in, delta Q3 charge went out, and delta Q4 charge also went out. So algebraically what I'll do, charge going in, I'll take that as positive charge. We can assume reverse as well. So since I'm assuming when the charge is going in, that's a positive. So here also it is positive. Here the charge is going out, so this I'll take as negative. And here also the charge is going out, so I'll take it as negative. So at any joint or any point, whether it is a joint or any point onto a single wire, charge density is always conserved. It does not change. And if I'm assuming initial charge density to be 0, it will remain 0 throughout. It is not going to change. So in delta t times, some of the charge going in, some of the charge is going out. So net charge going in has to be 0. So what we will do, net charge going in or net charge going out, it has to be 0. So I'll calculate Q net charge going in. So net charge going in is delta Q1 plus delta Q2. Both of these charges are positive because they are going in. Minus of delta Q3 because this charge is going out. Minus of delta Q4, this charge is also going out. And all this has to be 0 because the conservation of charge. Charge cannot be created, it cannot be destroyed. So let's put the values of delta Q1, Q2, Q3 and Q4 from this. So if I do that, I'll be having I1 delta T plus I2 delta T minus I3 delta T minus I4 delta T, and that is equals to 0. If I take delta T common, and since we know that delta T is not 0, since delta T is not 0, it means the only thing which is 0 will be I1 plus I2 minus of I3 minus of I4. That will be 0. So this is your first law of Kirchhoff's first law. So at any junction, the algebraic sum of current is always 0. Algebraic sum of current is always 0. That is your first law of Kirchhoff, and it comes from conservation of charge. And when I say algebraic sum, I mean you have to assume the directions. So the current is a scalar quantity. We don't assume the direction corresponding to that, but here we have to take that because the current going in and current going out both are having different feelings, different sense. So if current going in I am assuming positive, in that case current going out I have to take as negative. So you see, I1 going in, positive I1 plus I2 minus I3 minus I4, and that is equals to 0. So at any junction, the algebraic sum, this is the sum I am talking about. You can see this is a minus, but ultimately this minus is nothing but plus of minus I3. Here also it is nothing but plus of minus I4 because we are talking about the algebraic sum. So it is the minus I3 current which is going in. I3 current is going out. We can say since I3 current is going out, reverse of that is going in, that is a minus I3 current. So when we take the algebraic sum, it is the I1 plus I2 plus of minus I3 plus of minus I4, and that is equals to 0, and that will give you this equation. So see, you will always get, you can always create a equation at each and every joint using the relationship between the current going in and out at that joint. So this way you can get multiple equations whenever there is a complex circuit given to you, and you can make the relationship between the currents in different branches in that circuit. Okay, thank you.